on the open interval a to b, then this actually includes this. I will say there exists at least one c on the open interval such that, what's these? Or not. Such that f prime at c is equal to f at b minus f at a over b minus a. In the case b equals a, then it falls apart because we have division by 0. But the 0 case is taken care of here, if a is equal to b, or if f of a is equal to f of b. Here, what we have is f of a and f of b are at different levels. Again, we have a, we have b. Again, it's continuous on the closed interval, and the derivative is also continuous, which means, again, it's got to be smooth. It's got to be smooth. There's a nice simple arc that is smooth. Okay. And what is this? F of b minus f of a over b minus a. It's nothing more than the slope of the secant line. Because the coordinates here are b, f at b. Coordinates here are a, f at a. And the slope of the secant line is the change in y divided by the change in x. Namely, change in y over change in x. It's the slope of the secant line. What it says, there's some c in here so that the derivative at point C is the same as the slope of the secant line. And it doesn't matter if the derivative is defined at the endpoint, because it's on the open interval. On the open interval. For instance, if I look at y equals x to the 1/3 on the interval from 0 to 8. Y prime, 1/3 x to the minus 2/3, that is 1 over 3x to the 2/3. This is not defined at 0. Doesn't matter. Is it defined for anything greater than 0? Yes, it is. So this is defined on the open interval I know how to make it 0, I really do. It is continuous on the open interval 0 to 8. If I sketch this thing, 0, 0, 1, 1, 8, 2. Starts straight up and curves immediately this way. So, let's go on and find the point that satisfies the mean value theorem. This point, 0, 0. This point, 8, 2. The slope of the secant line is 1/4. So I want to find the value C here that makes this 1/4. That's easy enough. 1/4 is equal to 1 over 3 times x to the 2/3. Multiply both sides of x to the 2/3, and by 4 we get x to the 2/3 is equal to 4/3. If I raise both sides to the 3/2 power, x is equal, what's 4 to the 3/2? Square root of 4 is 2, 2 cubed is 8. 3 3/2, which is 8 over 3 times square root of 3. So, that's the x value. What's that? 1.73 times 1.7 is 5.1 about. 8 divided by 5.1 is a little under 1.6. So at about 1.6 in here someplace, it says that this slope is the same as that slope. The slope on the curve at 8 over 3 times root 3 is 1/4, as the slope of the secant line is 1/4. Now, we're not always able algebraically to solve that, because some functions are pretty messy algebraically, but we should be able to estimate that point if we're not able to solve it algebraically. So, that's all well and good. That's kind of all theory, but it allows us to work with a few problems. So let's work some of the problems in section 4.2, where we are searching for some of these things. So 4.2 is around 230, 235, I don't know. 270, 240. Wrong chapter. Go back. I was in the right chapter and turned away. Okay. 4, 4, 3, 4, 2. Oh, I want to look at that as well. So, let's begin with number 2, and it says, checking the mean value theorem, find the value or values of C that satisfy the mean value equation. F prime of C is equal to the slope of the secant line. Number 2 says f of x equals x to the 2/3, and we're on the interval 0 to 1. F of x equals x to 2/3, and we're on the interval 0 to 1. So we find f prime of x is equal to 2/3 of x to the minus 1/3, that is 2 over 3x to the 1/3. Okay. And the value of the function at 0 is 0, and the value of the function at 1 is 1. So the slope of the secant line is 1 minus 0 over 1 minus 0 is 1. So I want the derivative to equal 1 multiplied by x to the 1/3 equals 2 over 3. Cube both sides. X is 8/27. So if A is x is 8/27, f of x is cube root is 2, 2 squared is 4, cube root is 3, 3 squared is 9. So at the point 8/27, comma 4/9, the slope that is f prime at 8/27 is 1.
How do you get the 4/9? Sorry.
I plug this value x into that equation. And I said cube root of 8 is 2. Then 2 squared is 4. Cube root of 27 is 3. 3 squared is 9. That's where I got my 4/9. Plugged it into the original function. So that's the strategy on these first few. Number 6 says f(x) equals natural log x minus 1 from 2 to 4. From 2 to 4. Well, log x minus 1. F of x equals natural log paren x minus 1 on the interval 2 to 4. Okay. Let's find the slope of the secant line. F at 4 is natural log of 3. F at 2 is natural log of 1. What's natural log of 1? Zero. Divided by 4 minus 2 is equal to natural log of 3 over 2. That's the slope of the secant line. Now let's find the derivative. F prime of x is equal to 1 over x minus 1. Chain rule times derivative of x minus 1, but that's just 1, so it doesn't change it. We have 1 over x minus 1. And I want to find the value of x that is equal to that. 1 over x minus 1 is equal to log 3 over 2. Multiply by 2, multiply by x minus 1, multiply by, or divide by, we'll get there. 2 over natural log of 3 is equal to x minus 1. Add 1, 2 over natural log of 3 plus 1 is equal to x. So if I plug this value into the function, I will get the y. This is my c, but to get the y value, this is my c value. C is equal to, oh, what is natural log of 2 over log 3 plus 1 minus 1 close. Whew. One's that out. Natural log of 2 over log 3. Which is equal to natural log of 2 minus natural log of 3. Is that right? Because we had laws of logarithms. Natural log of the natural log of 3. log of A over B, you log A minus log of B. So this is the function value at this point, which will give us this slope. Okay, before we continue more problems on this page, I want us to think about a little physics. Have you concurrently enrolled in physics or have had physics the first? Well, this is going to lead into what we're going to do after the second test, somewhat. Position or displacement, S, is a function of time. Where I am depends on what time it is. But that position depends on also how I'm moving and whether I'm changing my velocity. So, another aspect, velocity is a function with respect to time, and acceleration is a function with respect to time. Turns out that velocity is defined as the first derivative of position. And acceleration is defined as first derivative of velocity, which is the second derivative of position. So if I put up here a equation, S equals 16 plus 48t minus 16t squared. Essentially, we have a starting position, a starting velocity, and a starting acceleration. Those may or may not change in time. Take the derivative of this, ds dt, velocity is 48 minus 32t. And if I take the derivative of that, the second s with respect to time squared, or dv dt, which is acceleration, is negative 32. Most of you recognize that perhaps as the acceleration due to gravity in feet per second squared. So this is modeling something beginning at 16 feet high, being thrown or projected upward at 48 feet per second. And this is its velocity. 48, it starts slowing down. After a second and a half, it quits going up, because it'll be 48 minus 48, 0, and then it'll come back down. So in 3 seconds time, it'll be back where it started. Trivia question, how long, or let me say that again, how high must you jump in order to stay in the air a full second? And the answer is surprisingly little, but at the same time, not so little. 4 feet. So if you have a vertical leap of 4 feet, you can be in the air for a full second. Now, how many of you have a vertical leap of 4 feet? There are not any NBAers that stay in the air for a full second. Some of them have a lot of hang time. But you know, when you're 7 feet tall, it looks like you're 11 feet in the air, and you're not. Your hands are 12 feet in the air, but your head is usually around the rim, 10 feet. Which means their feet are about 3 feet. So they don't stay in the air for a full second. Although when they take off, it seems like about half court and float all the way down and drop that ball in the basket. It makes it look so easy. Unless you're the Thunder of recent weeks. So, if we're given a position equation, we can find velocity and acceleration. But what if instead of position, we're given an acceleration equation and some initial conditions on velocity and position? Let's think about that for a moment. If I have acceleration is equal to negative 4.9, negative 9.8. Basically, I'm switching units from SAE to metric. Acceleration due to gravity in the metric system is about 9.8 meters per second squared. And let's say at time 0, V naught, that's velocity at time 0, is, well, I don't know, let's say 19.6 meters per second. And let's say position, S naught, S at time 0, is 39.2 meters. I want to start with this and come up with these. Now, if I knew the entire equation here, I could take derivative to get to here, derivative to get to there. So I want to do what we're going to call an antiderivative. We're going to undo the derivative. So I want you to think about what function has a derivative equal to negative 9.8. Can't look over the other board. We went from negative 32 on the bottom line to negative 32t on the line above. So if we start with negative 9.8, can you think of a function whose derivative is negative 9.8? Sure, that function is negative 9.8t. But wait a minute, that isn't entirely true. Because, let's look at these functions. Y equals x squared. Y equals x squared plus 7. Y equals x squared minus 76. Y equals x squared plus 0.00001. In every case, what is the derivative? In every case, y prime is equal to 2x. If we drew all these functions, they would be a set of nested parabolas. Each parabola has exactly the same shape, so at exactly the same point, x value, they would have exactly the same slope. So when we're looking for an antiderivative, we look for one that we know works, but it varies by some constant. That's where these come in. At time 0, I want this to equal 19.6. So if I plug 0 into here, what do I have to add to get 19.6? Oh, 19.6. So now I have the velocity equation that satisfies the acceleration and the initial velocity. Similarly, I say what to get position. Just looking at this first term, what function has a derivative negative 9.8t? You can look over the first two equations on the right. negative 32t became what? Negative 16t squared. So what will negative 9.8t become?
We have 4.9t squared.
Negative 4.9t squared plus some constant, but we're going to roll it into another constant as well, because what derivative gives you 19.6? We went from 48 up to what? 48t? 19.6t. And at time equals 0, I said we were at 39.2. So I was able to start with an acceleration, find a candidate for the velocity, and pin that candidate down by having a initial condition. And similarly, I have a candidate for position, and I pin that position down by an initial value. So we'll be solving equations like this in the not too distant future. But for some reason, in this section 4.2, they mentioned that well, if you can find derivatives, you can kind of figure out what they came from, barring an equivalent vertically placed function. All these functions are identical, differing only by a constant. All these functions are identical, differing only by a constant. The difference between the first one and the last one, you would have to have a fine pen to separate those two out. But these others are a little broader separation. What was that? 83 units apart. Okay, back to the problems again. Let's look at, we did number 2 and 6. Number 10 is coming up. Which of the functions of exercise 9 through 14 satisfies the hypotenuse of the mean value theorem on the given interval, and which do not? Give reasons for your answers. Number 10. Fx equals, what does that say, 4/5? X to the 4/5? Fx equals x to the 4/5. What was the interval?
0 to 1.
0 to 1. Okay. This is continuous, 0 to 1, no problem there. When we take the derivative, however, f prime of x is equal to 4/5 of x to the minus 1/5, or 4 over x to the 1/5. That is undefined at 0, but 0 is not in the open interval. So we're good. This, the mean value theorem, is satisfied by this. What is happening is, at the point 0, 0, this function is going straight up and immediately curves to the right as it climbs. But it satisfies the mean value theorem. Number 14. Oh, piecewise. How can a piecewise function possibly satisfy this? Well, if the pieces fit together, it's continuous. And at the point where they fit together, if they have the same slope, then the derivative is continuous. You know, if the functions don't fit together, end of story, it doesn't meet the mean value theorem. If the functions fit together, but the slopes at that point are different, it doesn't meet the second condition, that the derivative is continuous. So not only do they have to be at the same point, they have to have the same slope at that point. So let's look at this piecewise function and see if we can accomplish that. Number 14 says fx equals 2x minus 3 or 6x squared minus x squared minus 7. Ooh. 2x minus 3 or 6x squared minus 7. I would say minus, let's reread that. Second part says 6x minus x squared. Six x minus x squared. Usually you write these in either ascending or descending order. They did not do that here, but it's still a function. And this is my f of x. And this is from, what, 0 to 2? And the second part was from 2 to 3. Is that what it said? Mm-hmm. Ooh, wow. Yeah. Well, let's first see is f of x continuous. F of x is continuous only if at the end of this piece matches the beginning of this piece. Let's plug in. 2 times 2 is 4, minus 3 is 1. Let's plug in. 6 times 2 is 12. Minus 4 is 8. Minus 7 is 1. So we have the point 2, 1. We have the point 2, 1. The function is continuous. Let's find the derivatives. Derivative is 2 on the interval from 0 is less than or equal to x is less than or equal to 2. And is equal to 6 minus 2x on 2 is less than x is less than or equal to 3. Well, is this continuous? And again, we test it where they coexist, hopefully. And on the first piece, it's 2 everywhere. On the second piece, when x is 2, we have 6 minus 4. 6 minus 4 is 2. 2 equals 2. So they are joined at 2, 1. And at that joining point, they both have a slope of positive 2. So it is continuous on the closed interval, 0 to 3, and continuous on the open interval, 0 to 3. So this meets the conditions of the mean value theorem.
I have a question.
Yes?
On the second part of it, when it says x is greater than 2, why can you put 2 into it then?
Well, we're looking at the boundary. And even though we're defining 2 for this part, what is the limit of this part as x approaches 2? 2. And it's 2. Now, since there's nothing, we don't have division by 0, we don't have to divide out zeros, we can do it by direct substitution. So if we go think back to when we're looking at limits and how they behaved, if we had a 0 in the denominator but the same 0 as in the numerator, then we can divide those out. And then before we divide them out, it's undefined. We don't know what it is. But when we divide those out when they're not 0, then we say what is the limit as it approaches whatever value it's supposed to approach. In this case, 2. What is this value as x approaches 2? The answer is 1. What is this value as x approaches 2? The answer is 1. What is it? Well, I should say from the lower side, from the upper side. From the lower side, from the upper side. But if the value from the lower side is the same as the value from the upper side, then then it's continuous at that point. Okay. Let's see, next up, number 18. Suppose that f double prime is continuous on the closed interval AB, and that f has 3 zeros in that interval. Show that f double prime has at least 1 zero in AB, and generalize the results. You know, they often use the term generalize. I wonder if they use the term privatize, corporalize, sergeantize, lieutenantize, captainize, majorize, colonelize, generalize. So we're generalize the results. So we're told f double prime of x on the interval AB is continuous. Okay. And that f of x has at least 3 zeros. So, I'm going to write this as g of x times x minus c times x minus d times x minus e, where c, d, and e are all on the interval AB. Let's say this is A, let's say this is B. The function does something and ends up somewhere, but it has to cross that 1, 2, 3 times. So this is a sketch of what f might look like. It may have it may look that bad, but we don't care. What we care about is the simplest one we can draw that has 3 zeros. And that was what we had before, a nice smooth curve here, a nice smooth curve there. Disregard the snow-capped mountains and the choppy water pond. So, if this is f, and it's continuous on AB, and it has 3 zeros, then between these 2 points, Rolle's theorem applies. There has to be a point where we have 0 slope. And still, Rolle's theorem applies here between these 2 points. There has to be a point that has 0 slope. Might be that point. A, B, C, D, F, G. Let's skip F. H, G. Because we're using F already. So, F prime has at least 2 zeros. Let's draw a graph of F prime. And again, let's make it as simple as possible. 2 zeros. G, H, I, J. Still on the interval A to B. Okay. Again, I don't care what it does over here. I don't care what it does over here. I know it has at least 2 zeros. Again, keeping it as simple as I can possibly do it. Rolle's theorem says it has to have a place where the derivative of the derivative is equal to 0. So that says there's at least one point, what am I up to? I, J, K, F, double prime at K equals 0. Kind of interesting. If all the derivatives are continuous, and the first function has 10 zeros, how many zeros will the first derivative have? 9 zeros. And the second derivative, 8 zeros. And the third derivative, 7 zeros. And the 11th derivative, 0 zeros. So that'd be generalized. If the original function has n zeros, f prime will have n minus 1 zeros, and f double prime will have n minus 2 zeros. If they're all nice, smooth, continuous functions. And if f is a nice, smooth, continuous function, it does not guarantee that f prime is a nice, smooth, continuous function. Point made. Y equals x to the 1/3. Y prime is 1 over 3x to the 2/3. Nice and continuous. Division by 0 occurs at 0. It's still continuous, but it's not defined everywhere. Draw a sketch of that. I'm flying in here, up there, and out that way. It goes through A2, -8, -2. So, if it's not defined here, it won't be defined at y double prime or y triple prime or at y anything more prime, because the x power in the denominator just keeps growing. So we'll always have that. But if we don't have that situation, if they're all nice in the first, or the original, and the derivative of the derivative, each one will have one less zero than the one before. Okay. That's what they're trying to get us to realize, that maybe that was the case. All right. Number 22. Number 22, it says, show that the functions in exercises 21 through 28 have exactly 1 zero in the given interval. So number 22, f of x equals x cubed plus 4 over x squared plus 7. Equals x cubed plus 4 over x squared plus 7. What's it?
Yeah, that's it.
And we're on the interval negative forever to 0. Well, open interval at 0. Why is it open at 0? Because 0 is an asymptote. And it says, show that this has exactly 1 0. Let's look at the derivative. F prime of x equals 3x squared minus 8 over x cubed plus nothing. cubed plus 4x squared plus 7 on the open interval, negative infinity to 0. The answer here is, examine the sign of that. No matter what x is, other than 0, x squared is always positive. Since we're on the interval, on the negative side of 0, x is negative. What is x cubed if x is negative? Negative. And what is the opposite of a negative? Positive. Aha. So this is always positive, this is always positive, their sum is always positive, means this function always has a positive slope. Always going uphill. It doesn't say how is always going uphill, but it's always going uphill. Okay. So now how do we prove that has at least one zero? Or exactly 1, 0? The answer is we have to show two values of x, or find two x's, one of which f of x is positive, and one of which f of x is negative. If you're always going uphill to get from the negative side to the positive side, you have to cross the axis. And since you cannot turn around and cross it multiple times, because the slope is always positive, you cross it only once. So let's find some values that one gives us a negative, another gives us a positive. Well, if I pick a number like, well, I don't know, 1. One squared times 3 is 3. 1 cubed, I'm sorry, negative 1. 1 squared, oh, look on the back, 1. Now look at 1 in this. I'm looking at negative 1. Negative 1 is negative 1, plus 4 is 3, plus 7 is 10. So 1 point is negative 1, 10. Clearly that's a positive value. Well, let's pick a extreme point. Let's try negative 10. Negative 10 cubed is negative 1,000. Plus 7 is negative 993. Plus 4 hundredths is negative 992.96. If I did my arithmetic right. Do I have a value below the axis? Do I have a value above the axis? And the only way you can get from below to above is you have to cross the axis. And since the slope is always positive, it cannot turn back and cross the axis again. So this function has exactly 1, 0. I don't know what that 0 is. Takes a 5th degree equation to solve that. And by the way, the Swedish mathematician Abel proved that there's no general solution for 5th degree polynomials. 1st degree polynomials is linear equation, they're easy to solve. 2nd degree polynomials, quadratic, they're easy to solve. 3rd degree polynomials, cubic. There is an equation that you can plug in to find all 3 zeros, but it's not commonly taught. You can find it on the web. There's also one for 4th degree polynomials, and it's even more complicated than a 3rd degree polynomial, but they were solved reasonably close together by Italian mathematicians trying to think who got credit for it. Cardan, C-A-R-D-A-N. But the guy who really did it was Tartaglia. Tartaglia was kind of interesting looking because when he was a child, he was cut with a sword, ripped his mouth open. They left him for dead. Family dog kept licking the wound, keeping it immunized, healed up. Kind of ugly though. So any picture you see of Tartaglia, you don't see the ugly scar because he looks like him. Has the beard to cover the scar. But Viete and Tartaglia were students of Cardan. Now, I want to say Viete solved the cubic. No, Tartaglia solved the cubic and Viete solved the quartic. Don't quote me on that, but it's those three guys, Cardan, Viete, and Tartaglia, were involved in coming up with the equations to solve third and fourth degree polynomials. And Abel from Sweden proved that there's no general solution for fifth degree polynomials and above. Yes, some fifth degree polynomials are easy to solve, like x to the fifth equals 1. I can solve that. But not all of them are that easy to solve. Okay, going on, that was number 22. 26 is similar. R of theta equals 2 theta minus cosine squared theta plus root 2. Okay. 2 theta minus cosine squared theta plus root 2. And again, they say, this is still in the section that we want to show that it only has one zero. And this is on the interval from negative forever to forever. Well, if we kind of think about what this thing is, R of theta. Even though it uses R, this is not a polar equation necessarily. But let's think about the pieces. Disregarding those, 2 theta means it's a line with a slope of 2 that goes through the origin. Plus root 2 means it's a line that goes through square root 2. The maximum value this can be is 1 or negative 1. How much is square root 2? 1.4. So the vertical separation between these is 1.4. So whatever this is doing up here, it will not reach that line. But the question is, what is the slope doing? Because what if I have something like that and it crosses several times? So we have to look at the derivative of this to decide what's going to happen. Derivative, r prime of theta equals 2 minus 2 cosine theta, let me change that, minus and minus, times derivative cosine theta plus sine theta plus 0. Well, this is 2 plus sine 2 theta. R prime of theta equals. What is the range of sine of 2 theta? What is the range of sine? It is cradled between plus and minus 1. This is cradled between plus and minus 1. So this is cradled between 1 to 3. Minus 1 gives you the lower end, 1. Plus 1 gives the upper end, 3. This is cradled between 1 and 3. The slope is always positive. So it does not as it gyrates up and down that curve, it does not do so that much. I'll exaggerate here. Oop. And again, since the slope is always positive, we're good to go. And it's pretty easy to find a negative value and a positive value. Pick theta to be negative 2 pi. Cosine of 2 pi is 1. Cosine squared is 1. 2 times 2 pi is negative 4 pi. Negative 4 pi minus 1 is negative 5 pi, or negative 4 pi minus 1, down here someplace. And then on the other side, pick positive 2 pi. Then we end up with a similar situation up here someplace. So we have a positive value and a negative value, and there's one place where it crosses the axis. I don't know where it is, but we do have a place. Okay, let's look at section 4.3 for a little bit. My knees are screaming at me, so I'm sitting down, which means when I stand up at the end of class, they'll scream even more. But having said that, if we look at a function, if the slope is 0 at some point, and to the left of that point, the slope is positive, and to the right of that point, the slope is negative, what does it tell you about that point? Has to be a maximum. And if the slope of a function is 0, and to the left of that point it's negative, but to the right of that point it's positive, then that point has to be a minimum. So we have two other situations, and as an example, I'll say y equals x cubed. Y equals x cubed comes up, flattens out, and continues on. Didn't draw a very good graph, but at 0, the slope is 0. On the left-hand side, the slope is positive. On the right-hand side, the slope is positive. So if you go positive, 0, positive, you have neither a max nor a min. And if we take the opposite of that function, as an example, comes flying down, flattens out, continues on down. Slope of 0 at 0. It's negative on the left, negative on the right. So basically the first derivative test at a critical value, that is, at a value where the slope is 0. When we change from positive to negative, it's the maximum. If it changes from negative to positive, slope is the minimum. If it stays positive or stays negative, then that is neither a maximum nor a minimum. So, turning to the sections in 4.3, and those rules are on page 239. It lists the rules there. And go in terms of the problems, page 241, and we have, I'm looking at number 16, and 16 is a drawing. Okay. I don't much care where the points are, we can talk our way through it. We have up, down, up, down, up. Okay, and it's closed interval. All right, so let's just all right. Is it closed? Yeah. All right. First lesson, I identify all the critical points. I'll go on and throw some axes on here just for fun. It doesn't matter so much. But let's say this is the axis. Then we have intercepts, which help in graphing, but don't really help in finding max and mins. We have derivatives. This point gives me a slope of 0, this point gives me a slope of 0, and this point gives me a slope of 0. And we can examine those points coming into, let's call this one A. Coming into A, we have positive slope followed by negative slope, which means that's a max. Coming into B, we have negative slope followed by positive slope, which means this is a min. This last one over here, C, coming into it, we have negative slope. Going away from it has positive slope, so it says it's a min. The guy in question, which we don't find using the derivative, except noting the derivative is undefined at that point. We have a cusp. It is continuous, and if we check the slopes, positive coming in, negative going out, is the maximum. By inspection, the cusp is the absolute maximum on what we have shown. B is the absolute minimum. And we have two other points we haven't mentioned yet. This endpoint, A, B, C, D, is a min. And this endpoint, E, is a max. There's my absolutes, and everything else is a relative. So that's kind of what we were talking about in this section. Can we determine whether things are max and mins by observing the slope? And we don't have to draw the picture to observe whether it's positive or negative slope. All we have to do is plug in a value into the derivative equation. And often we don't even have to plug in a value. All we have to do is decide will the terms be positive or negative. So having said that, let's look at, I didn't mean to turn the page. Let's look at numbers. Oh, I think I want to start at number 30. And it says, A, find the open intervals on which the function is increasing and decreasing. B, identify the function's local and absolute extreme values, if any, say where they occur. K of t equals 15t cubed minus t to the fifth. Speaking of fifth degree polynomials, by the way, we can solve this one. Max equals 15, K of t. My goodness, what was that? K of t equals 15t cubed minus t to the fifth. Just for fun, let's find the zeros. When does this function equal 0? I'm going to factor a t cubed, and I have 15 minus t squared. And 15 minus t squared says my zeros are t equals 0 or t equals plus or minus the square root of 15. There are 5 zeros there. You see all 5 zeros? T equals 0, t equals 0, t equals 0. So we have a 0 of multiplicity 3, and there's my other 2, 5. So I have 5 zeros. This is a fifth degree polynomial we were able to solve. Boom, it's done. Okay? But we're supposed to find derivative to find where we have max and mins. So taking derivatives, k prime of t is 45 t squared minus 5 t to the fourth. Fourth degree polynomial, how many zeros? 4. Again, let's set this equal to 0 and solve. I'm going to factor 5 times t squared times 9 minus t squared. So our 4 zeros for the derivative is t equals 0, t equals 0, t equals plus or minus 3. So, let's look at the slope slightly left and right of 0. What's slightly left and right of 0? 1 and negative 1. If I plug 1 into this, I get 40. If I plug negative 1 into this, I get 40. That means it's positive on both sides of 0. So at 0, because 0 is a, but we have 0 slope at 0. But to the right of 0, the slope is positive. To the left of 0, the slope is positive. Oh, that's not positive. Positive. Positive slope coming in, positive slope going out. The point 0, 0 is neither a max nor a min. T equals 3. 3 cubed is 27. What is 15 times 27? What is 40 and a half? 430 and a half minus, what's 3 to the 5th? Uh, 343. So what's that difference? Let's plug in 3 cubed is 27. 15 times 27 minus 3 cubed, 243. This is positive. On the other hand, if I put in negative 3, I'm sorry. That's the function value. I don't care whether the function value is positive or negative. The slope is 0 at whatever this is. What did I say that was? 405. Twice. 20 times 15 is 300. 7 times 15 is 105. 405 minus 243. Okay, that's not so bad. 262. All right. Okay. So we have the point 3, 262. Is that max or a min? Well, let's plug a positive 3, a little over positive 3, and a little under positive 3 into this equation. This will be positive. A little over positive 3, this will be negative. A little under positive 3, this will be positive. So coming into this, positive, going beyond that, negative. So for this point, positive coming in, negative going out, means that point has to be a max. Looking at the other way, at negative 3, plugging in negative 3, we have the point negative 3, negative 262. And sure enough, at negative 3, again, this is positive. Slightly less than negative 3, that will be negative. Slightly more than negative 3, this will be positive. So at this point, negative coming in, positive going out, just a minute. So my 3 critical points, negative 3, negative 262 is a minimum. 0, 0 is neither a max nor a min. And 3, positive 262 is a max. By observing what the slope is doing slightly left and right of the known points. When we get to the second derivative test, this gets easier. But unfortunately, I said that would probably be today, but it will be after the test when we get to the second derivative test. Okay, let's do a couple of these more. That was number 30. Looking at 34, we have x squared times the square root of 5 minus x. X squared times the square root of 5 minus x. This one has a limited domain, a restricted domain because of the radical. G of x equals x squared times the radical 5 minus x. How do we find the domain? Rule 1, all real numbers. Except, there are 3 exceptions. Exception 1, division by 0. Do I have division by 0? No, not a problem. Exception 2, even roots are of negative values. Oh, 5 minus x must be less than or equal to 0. I'm sorry. Greater than or equal to 0. Add x to both sides. 5 must be greater than or equal to x, or x is less than or equal to 5. So there's my domain. So this function goes from 5 to negative forever. And at 5, easy to find is 0. 5 minus 5 is 0. 0 times square root of 0 is 0. 0 times 25 is 0. The y-intercept, when x is 0, we have square root 5. Square root 5 is just over 2.4. No, I'm sorry, that's not right. Yeah, 2.4 squared is 576. Closer to 2.2. 2.2 and change. 2.3 squared is 5.29. 2.2 squared is 4.84. So it's between it. So it's about there. Let's take derivative.
Okay, that squared would be 0, so it would be 0 multiplied by that. So it's 0
Oh.
would still be 0.
You're right, 0. I have a couple of zeros. Okay. Now, let's find derivative. G prime of x is product 2x times radical 5 minus x plus x squared times derivative of radical 5 minus x, and that is 1 over 2 times radical 5 minus x times minus 1. let's find where g prime is equal to 0. Here we have an additional problem. X cannot be 5, because then we'd have division by 0. Basically it says the derivative is undefined here. But what it means is that this thing starts off vertically one way or another. It may be vertical up or vertical down, we haven't decided yet. But I set this equal to 0, and if I multiply both sides through by this radical, I get 4x times 5 minus x squared. I think I made an algebra error this morning. I know I made an algebra error this morning. Let's combine like terms. Negative 4x squared minus x squared is negative 5x squared. 4 times 5 is plus 20x. And that's easy enough to solve. Factor of 5x, x plus 4. So it says at x equals 0, slope is 0. At x equals negative 4, slope is 0. What is the value at negative 4? 5 plus negative 4 is positive 9. Square root is 3. Negative 4 squared is 16. 3 times 16 is 48. Okay. So, if I pick a point slightly positive and look at this, for instance, I go to 1. Square of that's 2. 2 times 2 is 4. Over here, we have 1 over 4. 4 minus 1/4 is positive. So it's positive on this side, it looks like. Let's look at negative. I hate going negative 4 because that gives me that thing. Let's go at negative 1. At negative 1 we have square root of 6. Square root of 6 is about 2.4, between 2.4 and 2.5. Twice, 2.4, 2.5 is close to, plus another 2 in here. So, okay. Negative 2 times 2.4 is about negative 4.8. Oh. And this is positive, that's positive, so it's about 4.8 minus a fourth, still, or negative 4.8 minus a fourth is still negative. So it's negative on this side, positive on that side. You get far enough, it drops back down. And then it goes this way, and apparently that way, maybe. Let's check here. If I pick a large negative number, how about negative 20? Because that'll give me a nice thing in it. 5 plus 20 is 25, square root is 5. Negative 20 squared is 400, times 5 is 2,000. So at negative 20, I'm up at 2,000. So clearly it's positive slope, I'm sorry, negative slope on this side if I plug it into here, because that term dominates. So negative, 0, negative, that's neither a max nor a min. Minimum, we missed a point here. Oh, no we didn't. Let's go, where were we solving that?
be a negative in the
Got
bottom
that
where there's
five.
negative 5.
It should be x minus 4 instead of x plus 4 on the 5x.
Oh, here.
Yeah.
So that gives me x at plus 4 and x at 0. So at plus 4 we have it maxes out. Okay. Maybe, but anyway. Now, we have a very nice calculator which allows us to say